Hello friends, welcome you all on my YouTube channel JK Academy India. In this video, we will discuss about the synchronous machines. So, a machine in which following relation is maintained for its satisfactory operation is called a synchronous machine, and the relation is what? Ns equals to 120 F by P, where Ns is the synchronous speed of the machine in RPM, F is the supply frequency, and P are the number of poles. The machine may work as a generator or motor. So here we are discussing the synchronous machine. It may be a generator or it may be a motor. Because the working of principle as well as the construction of synchronous generator and motor are similar, so it is called synchronous machine. The same machine can generate AC power and same machine can work as a motor to drive the mechanical load. When a machine is to work as a generator, it has to run at synchronous RPM or speed to generate power at certain frequency F called power frequency. In India, its value is 50 Hz, whereas in UK or USA it is 60 Hz. When the same machine works as a motor, it can rotate only at synchronous speed. Since the magnetic pole are locked with the revolving field, if the machine fails to rotate at synchronous speed, it is called out of step and machine stops. Advantages of rotating field system over stationary field system. Only in a small synchronous machine, the field system is placed on the stator and armature winding on the rotor. But in large machines, the field winding is placed on the rotor and armature winding is placed on the stator. The rotating field and stationary armature system is preferred over satisfactory field and rotating armature system. Following are the important advantages of rotating field system over the stationary field system. First, armature winding is more complex than the field winding. Therefore, it is easy to place armature winding on stationary structure called stator. In modern alternators, synchronous generators, high voltage is generated. Therefore, heavy insulation is provided and it is easy to insulate the high voltage winding when it is on a stationary structure. Third, the size of armature conductors is much more to carry heavy current. Therefore, high centrifugal stresses are developed. Thus, it is preferred to place them on stationary structure. The size of slip rings depends upon the magnitude of the flow of current. Therefore, it is easy to deliver small current for excitation through slip rings of smaller size when rotating field is used. Fifth, it is easier to build and properly balance high-speed rotor when they carry lighter field system. The weight of the rotor is small when field system is provided on the rotor, and such friction losses are produced. Better cooling system can be provided when armature is kept stationary. So temperature rise issue of the synchronous machine can be avoided. Constructional features of synchronous machine. The important part of synchronous machine are stator, rotor and other miscellaneous. First is the stator. The outer stationary part of the machine is called stator. It has the following parts. First is the stator frame. It is the outer body of the machine made of cast iron, and it protects the inner parts of the machine. It can be also made any of the strong material. It can be also made any of the strong material since it is not carry magnetic field. Cast iron is only because its high mechanical strength. Stator core. The core is made of silicon steel material made from number of stampings which are insulated from each other. Its function is to provide an easy path for the magnetic lines of force and accommodate the stator winding. Third is the stator winding. Slots are cut on the inner periphery of the stator core in which 3-phase or 1-phase winding as per the requirement. Enameled copper wire used in winding the material. Second part is the rotor. The rotating part of the machine is called rotor, and construction point of view there are two types of rotor. One is the salient pole and other is the non-salient pole. So what is the salient pole type rotor? In this case, projected poles are provided on the rotor. The cost of construction of salient pole type rotor is low. Sufficient space is available to accommodate the field winding, but these cannot bear high mechanical strength at higher speed. Therefore, salient pole type construction is suited for medium and low speed, are usually employed at hydroelectric and diesel power plants as synchronous generator. Since the speed of these machines or generator is quite low, to obtain the required frequency, the machines have large number of poles as shown in this figure. So this is the path of magnetic flux shown by the dotted line. These are the field windings housed on the rotor. This is called the pole shoe, and this is the laminated pole shoe. This is the outer frame of the stator. Laminated stator core is used, and these are the air duct for coolings. To accommodate such a large number of poles, these machines have larger diameter and small length. For a speed of 200 rpm alternator coupled with water turbine, large water turbine, the diameter of machine is large, about 14 meter, and length is only 1 meter. The salient pole type rotor has the following important parts. So this figure shows the salient pole type rotor. These are the salient poles and this is the slip ring to connect the rotor field winding with the supply. The diameter of these rotors is very high, maybe 14 meter in case of hydraulic coupled generators, and length of rotor is around 1 meter. Spider. It is made of cast iron to provide easy path for magnetic flux. It is keyed to the shaft at the outer surface. Pole core, pole shoe are keyed to it, fixed to it. Pole core and pole shoe made up of laminated steel material, sheet material. Pole core provides least reluctant path for magnetic field, and pole shoe distributes the field over the whole periphery uniformly to produce sinusoidal waveform of the generated EMF. Field windings or exciting windings is wound on the former and then placed around the pole core. DC supply is given it through the slip. When direct current flows through the field winding, it produces required magnetic field. Now the damper winding. At outermost periphery, holes are provided in which copper bars are inserted and short circuited at both ends side by ring forming the damper winding. Generally the segments are on individual poles are joined together to form common rings, resulting in short circuited squirrel cage winding similar to that used in induction machine with squirrel cage rotors. Salient pole machines are frequently provided with a damper winding on the rotor to damp rotor oscillations during transient conditions and facilitate smooth operation under unbalanced load condition. So this is the salient pole type alternator mounted vertically at hydroelectric power plant. So this is the half sectional view. This is the outer casing and these are the internal parts of the synchronous alternator. A hydroelectric power plant usually having the silent pole type alternators are placed with their shaft in vertical position. Now non-salient pole type rotor. A non-salient pole alternator, in this case there are no projected poles but poles are formed by current flowing through it. Non-salient pole type construction is suited for high speed. The steam turbines rotate at high speed around 3000 rpm. When these turbines are used as prime mover for this machine working as generator, a small number of poles are required for a given frequency. Hence, these machines are smaller in dia and larger in length. Non-salient pole type rotors have the following parts. One is the rotor core. Rotor core is made of silicon steel stampings keyed to the shaft. At the outer periphery, slots are cut in which exciting coils are placed. It provides easy path to magnetic flux. Second is the rotating rotor winding or exciting winding. It is placed on the rotor slots and current is passed through the winding in such a way that poles are formed according to the requirement. So this is the non-salient type rotor. This is the field winding. These are the slip ring and this is pole. And this is the alternator picture, which is showing the rotor slots, stator slots, stator core, outer frame of the alternator and rotor. Air gap and its significance in case of synchronous machine. A very small air gap increases stray load loss, and synchronous reactance XD. A large air gap needs larger excitation current. Therefore, a compromise has to be made. Generally, the ratio of air gap to the pole pitch is in between 0.008 and 0.02. So this is the ratio for any synchronous machine: air gap to pole pitch. It is in between this. Now the most important part in synchronous machine is excitation system. Since the field winding is on rotor, a special arrangement is necessary to connect DC source to the field. In a small size synchronous machine, generally the field winding is excited from a separate DC source through slip rings and brushes. Slip rings are metal rings completely encircling the shaft of the machine but insulated from it. A brush rides and slips over each slip ring. The positive end of a DC voltage is connected to one brush and negative end is connected to another brush. In large machines, various schemes are employed to supply DC excitation to field winding. Some of the most important excitation systems are given here. DC exciters. This is a conventional method of exciting the field winding of synchronous generator. In this method, three machines, one is pilot exciter, second is main exciter, and main three-phase alternator are mechanically coupled and therefore driven by a common shaft. The pilot exciter is a DC shunt generator feeding the field winding to main exciter, and the main exciter is separately excited DC generator which provides the necessary current to field winding of the main alternator through the brushes and slip rings. Here you can see the picture. So this is the alternator, main alternator, and this is the field winding of the alternator. Field windings are connected to slip rings via carbon brush and supply DC power through this main exciter using a control rheostat. And this is the pilot exciter and showing the main field of the pilot exciter, and this is the field winding of pilot exciter. This conventional method of excitation suffers from cooling and maintenance problem associated with slip rings, brushes and commutator with the higher rating alternators. The modern excitation system have been developed by eliminating the sliding contact and brushes. This has led to develop static and brushless excitation system. So here we will discuss the brushless excitation system. First, we will show the figure. In this is the main generator shown through dotted line, and this is the field of the generator. The power generated from generator, and this is the bus fed to the generator bus. CT and PT are connected to measure the current flowing through the bus and PT to measure the voltage. That feedback is given to this regulator, and that regulator check the generating voltage and the current, and accordingly it adjusts and gives the firing command to the thyristor, and this is the field. So the main exciter field is being controlled by this regulator. The PMG is used to get the power for regulator. So in brushless excitation system, as we have seen in diagram, a brushless excitation system consists of an alternator rectifier, main exciter and pilot exciter, that is called PMG, permanent magnet generator. Both the main and pilot exciter are driven directly from the main shaft. The main exciter has a stationary field and rotating armature, which is directly connected through silicon rectifiers S1 to main alternator field. Thus the slip rings and brushes are eliminated. The main exciter's field is fed from a shaft driven PMG having rotating permanent magnets attached to shaft and a stationary three-phase armature. The AC output of PMG is rectified by three-phase full-wave phase-controlled thyristor bridges. The thyristor assembly is usually housed in removable drawers, which can be taken out easily for repair. The thyristor bridges are controlled by a set of dual firing circuit operating in parallel. The base excitation is controlled by an input setting to the thyristor gating circuit. This control signal is derived from the PMG via a regulated DC supply, which also serves the regulator logic circuitry. The regulator controls excitation by supplying a buck boost control signal, which adds algebraically to base setting. The regulator elements also comprise of solid state circuits. The excitation system has a short time constant and a response time of less than 0.1 second, or we can say 100 millisecond. Now we will see how the EMF is generated in the alternator. Generation of three-phase EMF. In three-phase system, there are equal voltage or EMF of the same frequency having a phase difference of 120 degree. The voltage can be produced by a three-phase AC generator having three identical windings or phases fixed on the spindle and displaced by 120 degree electrical. When these windings are rotated in a stationary magnetic field, as shown in this figure, these are the three windings, A1, A2, this is the one winding, B1 and B2 is the second winding, C1, C2 is the third winding. Here field is revolving. When windings are kept stationary and magnetic field is rotated, an EMF is induced in each winding or phase. These EMFs of same magnetic and frequency but are displaced from one another by 120 degree electrical. Consider three identical coils A1, A2, B1, B2 and C1, C2 mounted on the rotor. So this is the rotor, and now this is A1, A2, B1, B2 and C1, C2. Three windings are mounted on a rotor or placed on a stationary armature in the second circuit. As we have seen, A1, B1, C1 are the start terminals, whereas A2, B2, C2 are finish terminal of three coils. It may be noted that a phase difference 120 degree electrical is maintained between the corresponding start terminal A1, B1, C1. Let the three coils mounted on same axis be rotated, or the magnetic field system is rotated keeping the coil stationary is anti-clockwise direction at omega radian per second. Three EMF are induced in the coil respectively. Their magnitude and direction at the instant can be given as the EMF induced in a coil A1, A2 is 0 and is increasing in the positive direction as shown in figure C. This one. This is the wave diagram of A1, A2, B1, B2 and C1, C2 EMF. These all are 120 degree phase displaced electrically, and the coil B1, B2 is 120 degree behind the coil A1, A2. The EMF induced in the coil is negative and becoming maximum negative at point B1 and B2. The coil C1, C2 is 120 degree behind by B1, B2, 240 degree behind A1, A2. The EMF induced in the coil is positive and decreasing as shown in the wave. Now the phasor diagram. So this is the phasor diagram of the EMS induced in A1 A2, B1 B2 and C1 C2 all are 120 degree apart. Now from the phasor diagram, it can be represented by equation. Suppose EA1 A2 is equal to EM sin omega t, then B1 B2 will become omega t minus 2 pi by 3. 2 pi by 3 is nothing but 120 degree, and C1 C2 can be written as EM sin omega t minus 240. Now the EMF equation, let P number of pole, phi is the flux per pole, n is the speed in RPM, f is the frequency, ZPH number of conductors connected in series per phase, TPH number of turns connected in series per phase, and Kc and Kd. Kc is the coil span factor and Kd is the distribution factor. Flux cut by each conductor during one revolution, P phi Weber. P number of pole, phi is the flux per pole. Time taken to complete one revolution, 60 by the speed. So the average EMF induced per conductor will be P phi upon 60 N. Average EMF induced per phase will become P phi N to TPH upon 60, because the turn per phase equals to conductor per phase divided by 2. So the average value by multiplying the form factor for any sinusoidal wave is 1.11. We will get the induced EMF RMS value per phase will be 4.44 phi f TPH. TPH is the nothing but the turns per phase. Thanks for watching.